This is Mark Wilkinson from the University of Iowa Department of Ophthalmology and Visual Sciences. In this presentation, I will discuss ophthalmic optics and refractive errors of the eye. The diopter is the unit of measure used to describe the refractive error of the eye, as well as the power of ophthalmic lenses. A diopter is defined as a unit of lens power equal to 1 over the focal length of the lens in meters, or 100 over the focal length of the lens in centimeters, or 40 over the focal length of the lens in inches. In eye care, by convention, we work in quarter diopter units of power. Corrective lenses are either positive or negative in power. Negative or minus lenses cause light to diverge. Positive or plus lenses cause light to converge. I always find it interesting that the general public will call a plus lens a magnifying lens, but they never call a minus lens a minifying lens. This is what lenses do. They either magnify or minify the image viewed when a person holds a lens away from their face to view an object. However, as we will be discussing, when the lens is placed in the spectacle plane, or on the eye in the case of a contact lens, its role is to focus light on the retina by either adding converging power in the case of a plus lens, or diverging power in the case of a minus lens, to allow light entering the eye to focus on the retina. A person is said to be emmetropic or have emmetropia when parallel light rays focus on the retina with accommodation at rest. A person is said to have an ammetropia when parallel light rays are imaged in front of or behind the retina, again with accommodation at rest. Here you see an image of a schematic eye. For purposes of ophthalmic optics, the emmetropic eye is defined as being 22.6 millimeters in length and have a refractive power of 60 diopters. Myopia, also known as nearsightedness, exists when parallel light rays enter the eye and focus in front of the retina. Minus lenses are used in the correction of myopia. Negative, concave lenses are used to diverge the light rays entering the eye to move the focal point back to the plane of the retina. Hyperopia, also known as farsightedness, exists when parallel light rays enter the eye and focus behind the retina. Plus lenses are used in the correction of hyperopia. Positive, convex lenses are used to converge the light rays entering the eye to move the focal point up to the plane of the retina. Astigmatism can be described as the eye being shaped more like a football than a baseball. Astigmatism causes the light rays entering the eye to not come to a single focal point, as with simple myopia or simple hyperopia. In this case, there are two focal points corresponding to the two different focal powers of the eye. With astigmatism, there is one meridian with maximum power, known as the power meridian, and one with minimum power, known as the axis meridian. These two meridians are referred to as the principal meridians. Corrective lenses, either spectacle lenses or contact lenses, can be spherical like a baseball, where all radii from the center are the same length. Alternately, lenses may be cylindrical like a pop can. If you split a pop can vertically down the middle, you will have a flat side and a curved side. The flat side has no power. Finally, lenses may be spherocylindrical like a football. With a spherocylindrical lens, there is curvature and therefore power in all meridians. By convention, ophthalmology usually does their refractions in plus cylinder. Plus cylinder is noted on the phoropter in black numbers and in written prescriptions by a positive cylinder power. Optometry and opticians typically work in minus cylinder. In this case, the cylinder power is noted on the phoropter in red numbers and in written prescriptions by a negative number. What is important to know is that the actual prescriptions are the same. They just look different on paper. This difference can be confusing to our patients when they try and compare prescriptions that have been written in both plus and minus cylinder powers to each other. Because contact lenses and refractive surgery use minus cylinder, it is important to be familiar with both forms and to know how to convert between the two forms. More on that in a few minutes. You can deconstruct any spectacle correction by using an optical cross. To do this, make a cross and put the sphere power on the meridian of the cylinder axis. The cylinder power goes 90 degrees away from the sphere power. In the first example here, you see that the minus 1.00 diopter power is put on the axis orientation of 180 degrees. Next, add the sphere and cylinder powers together, In this case, combining the -1 diopter sphere power with the +0.5 diopter cylinder power equals -0.50 diopters. This power goes 90 degrees away from the sphere power, in this example at 90 degrees. In the second example, you see that the +4.00 diopter power is put on the axis orientation of 60 degrees. The sum of the +4.00 diopter sphere power with the +1.00 diopter cylinder power is +5.00 diopters. This power goes 90 degrees away from the sphere power, in this example at 150 degrees. It is important to know how to convert from plus to minus cylinder, as well as from minus cylinder to plus cylinder. To do this, in either direction, you will add the sphere and cylinder component powers together to get the new sphere power. Next, change the sign of the cylinder power from plus to minus, or minus to plus. Keep the same cylinder power number. Finally, change the axis of the cylinder by 90 degrees. Using the example of -1.00 plus 0.50, axis 180, first add the sphere and cylinder powers together to get the new sphere power. In this case, you have -1.00 plus a plus 0.50. This results in a new sphere power of -0.50 diopters. Next, change the plus 0.50 cylinder power sign to minus. Finally, change the cylinder axis by 90 degrees. In this case, 180 degrees minus 90 degrees equals 90 degrees, which is the new axis. Written all together, -0.50 minus 0.50, axis 090, is the same as -1.00 plus 0.50, axis 180. Let's review the various categories of refractive errors you will encounter. First, there is simple myopia. With simple myopia, the same amount of myopia is found in all meridians. For example, -2.50 diopter sphere. Simple myopic astigmatism occurs when there is myopia in one meridian and emmetropia in the other meridian. Here is an example of simple myopic astigmatism, -0.50 plus 0.50, axis 180. It is easier to see that there is only power in one meridian when this Rx is converted to minus cylinder. In minus cylinder, the Rx is plano, -0.50, axis 090. Compound myopic astigmatism occurs when there is myopia in all meridians of different amounts. An example of compound myopic astigmatism is -0.50 plus 0.50, axis 180. In this case, there is myopia of -2.50 diopters in the 180 degree meridian and -2.00 diopters in the 90 degree meridian. On the hyperopia side, there is simple hyperopia. With simple hyperopia, the same amount of hyperopia is found in all meridians. For example, +2.50 diopter sphere. Simple hyperopic astigmatism occurs when there is hyperopia in one meridian and emmetropia in the other meridian. Here is an example of simple hyperopic astigmatism, plano plus 0.50, axis 180. Compound hyperopic astigmatism occurs when there is hyperopia in all meridians of different amounts. An example of compound hyperopic astigmatism is +2.50 plus 0.25, axis 180. In this case, there is hyperopia plus 2.50 diopters in the 180 degree meridian and plus 3.00 diopters in the 90 degree meridian. Finally, there can be mixed astigmatism. In this case, there is myopia in one meridian and hyperopia in the other meridian. An example of this is -0.75 plus 1.25, axis 180. In this case, there is myopia of -0.75 diopters in the 180 degree meridian, and there is hyperopia of plus 0.50 diopters in the 90 degree meridian. Back to our schematic eye. Remember, the emmetropic eye is defined as being 22.6 millimeters in length and have a refractive power of 60 diopters. Now let's review some additional classifications of refractive errors. First, there is refractive myopia. Refractive myopia occurs when the power of the eye exceeds 60 diopters and the length of the eye is 22.6 millimeters. This is due to steeper corneal curvatures or higher lenticular powers. Axial myopia occurs when the power of the eye is 60 diopters, but the eye is longer than 22.6 millimeters. Every millimeter of axial elongation causes approximately 3.00 diopters of myopia. Refractive hyperopia occurs when the power of the eye is less than 60 diopters and the length of the eye is 22.6 millimeters. Axial hyperopia occurs when the power of the eye is 60 diopters, but the eye is shorter than 22.6 millimeters. The spherical equivalent is defined as the spherical power whose focal point coincides with the circle of least confusion of a spherocylindrical lens. The circle of least confusion is the midpoint between the two primary focal lines of a spherocylindrical lens. An example of a time when the spherical equivalent power is used is when an individual with a low amount of astigmatism is being prescribed a spherical contact lens. The spherical equivalent is calculated by adding the sum of the sphere power with half of the cylinder power. For example, with a spectacle correction of minus 3.00 plus 1.00, axis 180, the spherical equivalent equals minus 3.00 diopters plus half of plus 1 diopter, which equals minus 3 plus a half, which equals a minus 2.50 diopters spherical equivalent. Now you know how to convert a spectacle correction from plus to minus cylinder, how to determine a spherical equivalent power, and you know about the various types of refractive errors you will encounter when providing ophthalmic care.